schedule. Today's output devices. Then we have a very important recitation on Monday. I might have been saying every recitation is the most important one, but this one is particularly important because this is going to introduce machine building. And one of the goals of Fab Labs at this stage is the Fab 2.0 era, where instead of buying machines, you make machines. And so Monday's recitation will introduce machine building with a bunch of gurus. And then next week, the class is on machine building. And that's going to be a 2-week cycle. There's then going to be the April break. And after 2 weeks, as a group, you're all going to build machines. This week's class is getting ready for that in part. We're going to cover output devices. And so the individual assignment is add an output. And I'm going to talk about lights, displays, motors, actuators, switching power, and add an output device and make it do something. In the group assignment, we talked about test equipment last week. Group assignment is specifically to measure power consumption, which is a key question for output devices. So first note is electrical safety. This is a link to an organization for electrical safety. We're going to be going up in voltage, up in current, and this can become hazardous. So inside your body, a milliamp doesn't do anything. 10 milliamps is a shock and you lose control of muscles. 100 milliamps inside your body is enough for a heart attack and you die, which is bad. So to understand, you're getting from the outside of your body to the inside is mega ohms, but your internal connectivity is kiloohms. So in theory, you could kill somebody with a 9-volt battery by poking it into their skin. But you should also be aware of dielectric breakdown, which is a kilovolt over a millimeter actually discharges through any just about any material, and it breaks down. So one way you can get something that can be very dangerous is in power supplies. The power capacitors can store power for a surprisingly long time. So if you're ever working around a big capacitor, you should always be paranoid and discharge it by holding something insulated, a conductor that's insulated, like say a screwdriver. Inductive flyback is a motor looks like a coil. So if you switch current going through a motor, there's a magnetic field in here. When you open the switch, the magnetic field collapses and you get a big reverse voltage, and that can easily swing to very high voltages and can blow out components and be hazardous. If you connect high power wrong to a circuit, you can destroy the circuit. So you can put diodes to protect your circuits, but if there's much current, there's a drop across the diode. You can instead use transistors, and when you hook it up this way, it'll only conduct if you're above ground to protect your circuits from power. When you're dealing with higher voltages, the processors we're using and many of the sensors need to run at low voltages. And so a common need is to shift between high and low voltages. And again, you can use a MOSFET in this configuration And it's very clever. This page nicely goes through all of the cases of which side is higher and which is lower to show how this clever configuration lets you use a MOSFET to switch between high voltages that you might be using for power and low voltages for signaling. And then, let's see, many of the connectors we're using are unpolarized, which means you can connect them the wrong way. A slightly larger and more expensive connector can be polarized, which you can only connect one way, which is, when you go from prototyping to production, a good thing to do. And then these are all a range of circuit protection devices from DigiKey. So I would take away from that dealing with power electronics is much like machining. You don't do it by yourself in the middle of the night when you're tired. Don't do it with too much coffee or too little coffee. You need to be relaxed, at peace. Don't do it, crucially, with a messy workspace where there's a whole tangle of wires. Be mentally clear, have a clean workspace. Be careful turning things on to be ready to turn them off. It's similar to the kind of precautions we take for machining, but when you're working with power electronics. Oh, actually, there's a Nicholas, are you on? I should link on here your QC page. So we're going to be dealing with brighter lights, more powerful motors. We don't want to consume lots of batteries. So one way to power is with USB. And one of the great things is USB PD can let USB go up to high voltage and high current. Now, not all USB supplies can do it. Here, let me pull up. This is an example of a much heftier USB supply that can put out USB PD. And actually, there's something after this that goes up to 200 watts. And so in the world of USB PD, if you have a good USB supply, you can negotiate for power. Now, I think I can find this because he put it on his Fab Academy page. Nicholas. Oh boy, let's see. I should have thought to add this. Can somebody help me find Nicholas's QC page? Okay, Nicholas, you are here. So yeah, put in the chat the page I'm looking for. No, but Hank, I think Nicholas had a page after boot camp. Yeah, so between you find. So anyway, what you'll get when we find the missing page is. I love our chat GPT, and I'll add this to this page. It was so USB QC, USB PD is a standard. USB QC is a funny, not quite a standard. It's a proprietary protocol, but it's widely supported. Compared to USB PD, USB-C is much easier to implement. And so Nicholas has this really nice board using just a tiny 412. And most, this is a little confusing, most USB high power supplies know how to do both PD and QC. And so on the right is his board. In the middle is a USB power meter, which I'll talk about in a minute. And then with it, you can negotiate on the voltage and current. And so between those, I strongly recommend you can use USB supplies for all of your power electronics pretty much anymore. This is a vendor for power supplies. Switching ones are efficient but noisy. Linear ones are quieter but more expensive. And then these bench supplies let you pick a voltage and it'll tell you the current, or you can pick a current and it'll tell you the voltage. And so those are good for embedded supplies. When you need batteries, LiPo, lithium polymer batteries, are by far the most common. There's a common ecosystem for them. Charging those is non-trivial, but there are modules like these that manage the charging. And then something to be aware of is they are a fire hazard. You shouldn't keep them lying around. You should keep them protected in storage like this. And for extra credit, there you can send power wirelessly. So this is a classic paper, and there have been a number of related projects where you can, through a magnetic field, send power without wires over short ranges and slowly over longer ranges. So those are ways to provide power. Then to measure power, one way you can do it is, and let's see, let me step back to the reasons I want you to measure power. When you're using a motor, it's not hard to be more ambitious for the with your motor choice than your power supply choice. So the power supply can't handle the current the motor wants. If you want to make, say, a mobile cart with batteries, you need to know the power draw of your motor to size the batteries to keep up with it. So one way to do it is if you have a bench supply that has a meter for voltage and a meter for current, and then it has knobs to set each. If you connect it to your load, if you set the voltage at, say, 5 volts, then the meter will tell you how much current it's drawing. So that's one handy way to do it. A second way to do it is if you connect a supply to your load and you put a tiny resistor going to ground, like 1 ohm, and then if you measure the voltage across that, and the analog input to a microcontroller can do that, you can then sense the current going through it. Both of those requires getting into the circuit. Another way to do it is if you connect a supply to your load, the current through the wire makes a magnetic field. And so if you have a DC current, if you put a magnetic field sensor next to it, you can calibrate the strength of the magnetic field and get the current. And if you have an AC load that's varying, you can just wind a coil around it, and the varying magnetic field will induce a current in the coil, and you can sense it that way. So those are all ways for you to measure loads, which I want you to do to characterize one of your output devices. And so now we're off with output devices. So this is a basic signaling LED. And at this point, this is just simply a shou. I've got my current limiting resistor and I've got an LED. And at this point, you've seen I set the pin to an output and I can write to the LED in Arduino. And in MicroPython, I set the pin to an output and I set the value of the pin. Generally, I recommend using the Arduino environment when you're limited by performance and you need compiled C code, and when you're using Arduino libraries. Other than that, for ease of programming and programming flexibility, I really like MicroPython. And so this, I barely need to show it. It just, this is showing blinking the LED. Oh, but yeah, actually, yeah. So blinking the LED. I should go back. The one slightly non-trivial thing is for the ESP, you need to use Expressif's tool to load MicroPython if you want to switch to that. So here I'm loading MicroPython in it rather than using the Arduino IDE. And that takes it's quite a bit of code. And then once I've loaded it, I'll jump ahead. Then I can go in, and Thani is a nice environment. I can connect to it. And then now I'm talking to the Python interpreter. So I can type commands, but in particular, blink the LED. So that's pretty easy. Now, the most important concept for this week is PWM, pulse width modulation. So to switch loads like power transistors, remember that power is I squared R. So if a switch is open, there's no power consumption. And if you have a perfect conductor, there's no power consumption. But in between, if you have a resistor, there's power consumption. So we like R generally to be 0 or infinity. And so that means we want our power transistors to be all the way on or all the way off. And then PWM, pulse width modulation, is we make pulses and we vary the duration. So like in this example, I've got these chunks where it's on and chunks where it's off. But if I zoom in one, I've got equal on time and off time. In the other, the on time is short compared to the off time. And so by varying the fraction, if you have a very short on time, for example, an LED will be dim. If you have a long on time, it'll be very bright. And so we're not varying the voltage. We're either all on or all off, but we're varying the duration. And so here's first the example. I'm going to run this code. Oh, actually, sorry, I skipped over something. Let me show this. So if you're using MicroPython, so if you're using the Arduino environment, when you load the code, you just load the code. With MicroPython, you have the whole MicroPython loaded. And so there's two special programs, a boot PY and main PY. And it runs those automatically when you start. So I'm going to save this as main PY, and that'll make it run automatically. I'm going to load the program. And now you see the LED continuously varying intensity. So this is like when your laptop fades in and out. So what I'm doing here is in MicroPython, I'm using pulse width modulation that it knows how to do. I'm setting the off time versus the on time. And here I'm stepping over, making the pulses longer, so it's getting brighter. And then here I'm making the pulses shorter and it's getting dimmer. And so that little bit of code then gives me the fading LED. And then if you, your eye can't respond this fast, so your eye just sees the average brightness. Now, if you take a PWM LED and you wave it really quickly, you'll actually see the separate pulses because they're occurring at different spaces. So if you move your head quickly or you wave it, you can tell if it's being pulse width modulated. But if it's not moving, your eye just sees the average intensity. So that's PWM. And then Charlie plexing is a really neat idea. So here I've got an array of LEDs, and I'm driving them one at a time, slowly and quickly. And what I'm doing there comes from an app note from Charlie. And here's the idea there. Let me make a little array of LEDs. And I'm going to draw them as a square array, but it doesn't have, they can be in a line, they can be in a circle. Okay, now, naively, you would think I need one wire for every LED. So if I have N LEDs, I need N wires. Instead, here's what I'm going to do. I'm going to take a pin. I'm going to connect them to the cathodes in a row. And I'm going to connect them in the anodes in a column. So it's crazy. Each pin is a row and a column. Now, what makes this work is a pin can be off, it can be on, or it can be tri-state, which means it's disconnected. It's an input. So each pin can be either off, on, or disconnected. And so, first of all, the diagonal ones I can't use. So you don't actually put components there. But all the other ones, so let's say this pin is a 1, that pin is a 0, and this pin is an X. If we take the 1, the 1 is going here, and on the cathode side, the LED can only go in one direction. So the 1 going here and the 0 here, if we follow, let's see, the 1, we have a 1 here, we have a 0 here, and so this LED turns on. That's great. In addition, we have the 1 here, we have the 0 here, and nothing happens because the LED doesn't go backwards. And then all these other ones are, this one is just the tri-state, and so nothing turns on. So we turned on only one LED. And so what this means is, and you really have to draw this for yourself to get it. If I have N wires, I can control N times N minus 1 LEDs. The minus 1 is because I don't get the diagonal. And so that's, roughly N squared LEDs. So N wires controlling N squared. So what's going on this board is I've got each pin going to a row and each pin going to a column. And if you look, it's 4 by 5 because I'm not using the diagonals. And by switching, if I look at the code to do it, in the code, I'm taking turns setting pins to be inputs versus outputs. And I'm switching which pin is an input and which is an output. So Charlie plexing lets you control many more LEDs. And these could be in a straight line. They could be a bar graph. They don't have to be in a square array, but it lets you control N squared, roughly N squared LEDs with just N pins. So that's Charlie plexing. This is an RGB LED. In it, are three LEDs, and they can either have a common anode or a common cathode. And so the board consists of my three LEDs. I've got three current limiting resistors. And you'll see one is smaller. That's because the blue LED is less efficient than the green or red ones. And so now I'm going to PWM. But now the PWMing, I can control which LED I'm talking to. So I can go red, green, blue, and then I can do all of them for white. So this part is essentially 1 pixel from a Jumbotron display and lets you make color change. Okay. Now we get to MOSFETs, which is the main topic for today. So what I'm going to cover next is this is a much, much brighter LED. This one is so bright you can't look at it max out. Max current for one of these is 150 milliamps, but our processor pin can only do 50 milliamps. So we need help, and that's where the transistor comes in. So we're going to be using MOSFETs, and I covered this quickly last week, but let's do it a little more slowly. So we have two kinds. We have the N MOSFET and we have the P MOSFET. So that's the N MOSFET. We have the P MOSFET. They both have a gate that controls it. Then they have a source and a drain. The drain gets connected to the load, and the source gets connected to the supply. So for an N MOSFET, the source is ground. For a P MOSFET, the source is the high end of the power supply. And then for an N MOSFET, it sinks current. The P MOSFET sources current. And so we use that as a switch. These two notes are when you connect a MOSFET, you might see a resistor here, and you might see a resistor here. This resistor is for when you first turn on the processor before you program it. This pin is an input, so we don't know what the voltage is here. And so the MOSFET could turn on before you write any code. So this is, say, a 10K resistor. And what it does is it keeps the MOSFET turned off until you actually turn on the program. So it makes sure it's off unless you actually choose to turn it on. And again, this resistor here, when you turn on the MOSFET, you slam it on, which can make electrical noise and a big current surge. The MOSFET acts like a capacitor. So this is a fairly small resistor. It could be, it depends on the application. And the job of that resistor is to slow down the transition so it's not as noisy. So we're going to be using MOSFETs. And this is an example of one of the N MOSFETs that we'll make a lot of use of. This one goes up to 30 volts and 5 amps. And if you want to make things like a much bigger thing, this is a MOSFET that goes up to 90 amps. So that's enough for not an automobile, but like a e-bike or skateboard. So here's a board, and here's what's going on. Well, actually, let me show you what it's doing first. So here I'm PWMing, but I'm PWMing with these LEDs that are so bright that when they're all on, you can't even look at them. And one thing you'll see is I've got no current limiting resistors. The reason for that is an LED has a diode drop, and 2 volts is a typical value. It depends on the LED. If the diode drops add up to your power supply, you don't need a current limiting resistor anymore, because if you start to pull current and it droops, it automatically limits. So here what I'm doing is I'm stacking up the diodes in series to add up to my voltage drop. Then to add more of them, I'm making multiple strings in parallel. So I'm making each of these. I can't add more LEDs than the total drop because then it won't work. And so I add them up to the drop, and then I keep adding them in parallel. So I've got 3 strings of LEDs. And then what I'm doing is at the very bottom, so I've got all of my LEDs. At the very bottom, I'm then putting in my N MOSFET, and I'm going to use that to PWM the current to ground. So here's my drain connected to the load. Here's my source connected to ground. Here's my gate connected to the processor. And then at that point, all I'm doing is PWMing. So Ronald, do you want to share something relevant to what I'm talking about? Yeah, one note is with these bright LEDs, again, it can be so bright it can hurt your eyes. And there can also be a thermal runaway issue where as they get hotter, they can conduct better, which means they pull more current, which means they get hotter, and that can actually diverge, and you can have a fault from the temperature running away. But that introduces MOSFETs, and now we're PWMing bright LEDs. Next come displays. So this is an LCD display. And I'm going to use it to say hello world. These are still around, but I don't really recommend them anymore because of OLEDs and TFTs. So there are these cheap and cheerful OLED displays, a few dollars each. This is a bitmap display. It's actually many tiny organic LEDs, and you can control each one separately as a pixel. So this is 128 by 64 of them. And so I'm going to show you 2 ways to do this. Yeah, so in fact, the LCD I'm showing is with an I2C. This is an example where I'm saying hello world and I'm have text and I'm counting. And here's a version where I'm going to be doing the same thing. So I'm putting text on and I'm updating a bar graph and I'm updating some numbers. In this version, I'm doing it in MicroPython, and it's beautifully simple. I'm using an let's see, the SSD 13.0 chip 06 is a common chip used to drive these, and there's libraries. There's multiple libraries for it. Here I'm using a MicroPython library for it. With that library, all it takes is I import the library. I'm connecting it with I2C. I'm going to talk more about this in networking. I2C has 2 pins, SCL and SDA. And what the crucial thing you need to know about I2C is SCL. Actually, let me give myself some more room. So SCL and SDA are the pins in I2C. It's a clock and a data pin. They need pull-up resistors somewhere between 1 and 10K. And typically, those resistors are on breakout boards if you buy a breakout board. If you make your own circuit, you need to put the resistors in. So in this example, I'm using the module that has the pull-up resistors. So if we go to the board, I just need to connect SCL and SDA. Oh, actually, sorry. In this case, I'm putting the pull-up resistors on it. So here are the two pull-up resistors on SCL and SDA. And then I'm connecting it to the Xiao I2C pins. And then all I need, oops, wrong link. All I need in the code is beautifully simple. I just say I'm going to connect to I2C. Then with the OLED library, I'm going to connect to the OLED. And then I put out text and I put out a rectangle and I show it. Yeah, there's a note. You shouldn't add, you should only have one set of pull-ups on an I2C bus. You shouldn't have multiple ones. Otherwise, you start to fight against the pull-ups. So this is all it takes to in MicroPython to drive the OLED. Now, this example down here, I don't recommend as a beginner, but in this example, I'm doing the whole thing with a tiny 412. And that's not nearly big enough to run one of the big libraries I showed you. Here, I do the whole thing from scratch. So this is I2C, and I'm doing I2C in software rather than hardware. These are the font definitions. And the way I made those is, believe it or not, GIMP can actually output C code. The image processing can write code. And so this is code from GIMP for the character generator. And then here I'm implementing the OLED protocol. And then once you get through all of that, now this looks like the Python. I'm just putting out the text. But in this file, I'm actually showing there's no library under the hood what you need to talk to the OLED. So cheap, cheerful, few dollars, bitmap display lets you put out text. So great option. Then there's a competition between OLEDs and TFTs. Roughly, we use TFTs for bigger displays, but you can get OLEDs all the way up to high-def, large-scale TVs. So there's a sort of a race between cost and size for OLEDs and TFTs, but roughly the TFTs tend to be more available at bigger sizes. And so on this example, here I'm using SPI instead of I2C. And again, we're going to cover these protocols more in networking week. And so with that, I then, here I'm not using my own code. I'm just using a demo code for one of these libraries. And so on the TFT, now the demo code is running through all these displays of all the different things you can do on the TFT. So all of that was using this library. And let's see, let me come back. There's a few standard chips that are used to connect to the TFTs. This is a common one. And then this is a library that knows how to talk to multiple of the common chips. And so with that, then it then has support for all the modes I showed you. A last thing, emerging e-ink, which actually came from a researcher who started in my lab many years ago. The difference between e-ink and OLEDs and TFTs are e-ink update more slowly, but they're non-volatile. When you turn the display off, it retains the image without power, is the big reason to use e-inks. Okay, that's displays. I'm going to skip video because that's no longer common. And we're going to go to motors. So let's see, so here I am in the Arduino IDE, and I'm spinning a motor slow and fast, forward and backwards. Then I'm going to redo the same thing in Python. So here's what's going on there. This is one of the best parts you're going to meet in the class. We love these. Under $1 in quantity. And let's see. I'm not seeing the link to the data sheet. Okay. I'll add the data sheet to the page. So here's what's going on in there. The motor acts like a coil, and we need current to go in both directions if we want to go forward and backwards. We don't need this if you only want to go forward, but if you want to go forward and backwards, we need to go in both directions. And so to do that, you need to do this. So this is such a common configuration. It's called an H bridge because it looks like the letter H. So if this PMOS is on and that NMOS is on, current will go like that. If this PMOS is on and that NMOS is on, current will go like that. So that lets us pull current in either direction. And then if these two are on, it goes like that, and that actually acts like a brake and stops it. So the H bridge lets us put current in either direction. But there's a problem here, which is this could be, say, 24 volts, and we have a processor here that's running at 3 volts. The N MOSFET, we need to switch from 0 to 3 or 5 to go off and on. But this, we need to switch between 24 and 21. So we can easily turn it on, but we can't turn it off because we can't produce that 24 volts. So what's going on in this wonderful part is here's the H bridge that's going to drive our load. It's got what's called a charge pump. So we put in a low voltage logic signal. It generates the high voltage signal from that. It's got a comparator, so we can pulse width modulate in software, or we can set the current and it'll pulse width modulate in hardware. And finally, it's got sensors, and it won't let you put out too much current, and it won't let you overheat, and it protects your circuit. So all of that lets you make this, under $1 part. And for specs, this H bridge goes up to 3 amps and 44 volts. And that's enough, for example, for the biggest machine tool in your shop. Like a ShopBot, that's enough for. And so on the board, I've got a Xiao. And here's my H bridge. And then you'll see a couple things about this board. One thing is you'll see I have fatter traces. This is an example of a trace width calculator that helps you figure out when you're pulling a lot of current, the resistance in the traces becomes an important limitation. You dissipate power and they heat. So for higher current paths, and for this example, I don't really need it, but I'm using it to illustrate. For higher current paths, you can use heavier traces. The second thing going on is there's a thermal pad underneath, and I'm using that just to help couple heat away. And then you'll see I've got these 2 extra capacitors. So here's my H bridge. It's connected to the high voltage supply. I've got it connected to the logic supply. When the H bridge switches, there's a big spike on the power. So I've got connected to it. This may seem like it doesn't make any sense. I've got 2 capacitors in parallel. I've got a 0.1 and a 10 microfarad. But the reason this works is these respond on different time scales. So the job of the smaller capacitor is when there's a spike in the power line to couple that, to help clean up the power. The job of the bigger one is when the H bridge is asking for current, it helps provide current before it can come. The power supply at a distance has inductance. And so the local capacitor helps with the surge of current before it comes in. If you don't use those, sometimes everything works, but one symptom is your processor can reset, which is very hard to debug, and the motor can be unreliable. The motor can be jittery. But once I do those things, if we look at the code, on the H bridge, it's got a very simple logic diagram. It's got 2 pins going in, so it can be off, off, on, off, off, on, and one on, the other off, it goes in one direction, one off, the other on, it goes in the opposite direction. So if we look at the code for this, in turn, I'm turning one of the input pins off, the other pin on, and I'm PWMing. And then I'm going to do that at a slow rate and then at a fast rate. And then that's controlling the code. And I've got one other thing going on here. If you're using MicroPython, when it turns on, it runs boot py before it runs your code. And you'll see in here, I'm using boot py to make sure the pins are output and the H bridge is turned off. If I didn't do that, before my program starts running, the motor could go crazy. And so in MicroPython, I use it to make sure it turns on reset. In Arduino IDE, here's the similar code. Here, what I'm doing is, this is, again, I don't like this, but Arduino calls PWM analog write, except for on processors that have a digital analog converter where it's not PWM, it gives you a voltage. It's confusing. But here I'm using analog write to PWM, and then I'm doing the same thing. So that's using an H-bridge to drive a DC motor. Some things to know about DC motors are, if you look at their efficiency versus RPM, it looks like that, where they're happiest at, say, 10,000 RPM, and they're unhappy going slowly. So if you want a DC motor to turn slowly, you use what's called a gearhead motor that gears it down. And you can buy tiny DC motors that have a little weight on them that's unbalanced. And that's, if you want to get haptic feedback, you drive little tiny DC motors that have an unbalanced weight and they vibrate. Okay, need to keep moving. Now we're going to do audio. So you can drive speakers with analog signals, but a Class D amplifier is just, it's actually the same thing, meaning a speaker looks like a coil, just like a motor. So if you connect an H-bridge to a speaker and you pulse width modulate, you can produce audio. So I'm going to show you a few examples of that. So that's just beeping. In that example, I'm using exactly the same board, the Xiao with the H-bridge. The only difference is instead of a motor, I've got a speaker. So in that example, all I'm doing is ramping the PWM. Now I'm going to do something much more interesting. So here, I'll come back to the second part. So when you listen locally, you'll hear the tone sounds much nicer than the first one. What I'm doing here is what's called wavetable synthesis. So these are the music notes that I'm going to play. And then, well, actually, yeah, let me first finish showing the example because there's a lot to explain here. Hello world. Hello world. Hello world. Hello world. So now I've got the board talking. So that was the board, not me saying hello world. So what I'm doing here is what's called wavetable synthesis. So for the musical notes here, I'm looping over, let's see, if you look at musical notes on a staff in time, each of those corresponds to a waveform. And then we're going to vary the frequency of the waveform. And then the waveform itself consists of samples. So what I'm doing here is really powerful. I'm going to loop over the music notes. And then for the music notes, I'm going to loop over the pitches. And the pitches I'm using come from a table of the wave, the sine wave. So I'm going to make a table of sine wave pitches, and I'm going to play them out with PWM. Now, for the PWM, I'm doing something interesting, which is the RP2040 has a really powerful feature called the PIO. So if we get to the see, I want to go here. So the PIO in the RP2040 is, it actually has 8 of these little programmable processors, each of which can run 2 programs. So it's got all these little processors around the main processors. And then they run teeny little programs, but the programs they run very, very fast. And so you can use them to implement protocols. But what I'm doing here is this little bit of code is a program to be a pulse width modulator. This sets it up, and then this initializes them. And so this lets me make pulse width modulators that run as fast as the processor. And I'm running the processor here at 250 megahertz. And so to pulse width modulate, we had the notes, and one note turns into the waveform, but then one sample in the waveform turns into the PWM pulses for the current. So we've got 3 different time scales: notes, waves, and PWM. And for that to work, the PWM has to be at a very high frequency. So I'm using the PIO generators to make high frequency PWM generators. And then I'm using that to do the wavetable synthesis. And so in that first example, I was playing the sine wave. And then in the second example, this is me saying hello world. And in the second example, what I'm doing is I read in the file. Let's see. Yeah, I read in the file of me saying hello. And then all I'm doing is I'm pulling out samples of me saying hello, and I'm playing all of that out. And so with just the processor and the H bridge, we can make beeps. And just to make a beep, you don't need to do everything I showed you. Just simply the beep, you can just PWM with the built-in PWM. But with this wavetable synthesis, you can make, music synthesizers, you can control waveforms, you can play audio samples, all of that. And finally, this is such a common thing to do that this is a library. The Raspberry Pi Pico is the RP2040. This is a library you can use to play MP3 files. You can get little embedded modules to do that. Like this is a cute little module whose job is just to play MP3. But you can also do that with one of these libraries with the shell. Okay, so that's speakers. Solenoids are, I've shown this in some of the conversations. This is a nice video where he shows he's going to wind his own coils.
2 separate timers
and then PWM to the coils. And with that, he's going to make a xylophone. Okay, let's keep going. servo motors. Yeah, that's an X-ray from what's inside a servo motor. If we take, so these are motors where I'm controlling the angle. So servo motors, you put a PWM in, and it's slow. It's 50 hertz, and it's typically between 1 and 2 milliseconds controls the angle. The exact value depends on the motor. And then the board is really simple. All I'm doing is I'm putting out the PWM to a pin, and by PWMing, I control the angle of the servo. That's doing it with the D11. So servos are really easy to do. One thing you need to be aware of is they run on the supply voltage, typically 5 volts. And so depending on the size of the servo, you can need a substantial 5-volt supply for it. And so there's tiny servos you can use to move like an indicator, somewhat bigger servos, for example, for steering of a car or a flap for a plane. And then you can get huge servos for things like a sailboat. Okay, next is BLDCs. So here I'm going to drive a BLDC is a brushless motor. So a brushless, so the DC motor I showed you before, like the little toy motor, as it rotates, you need to keep changing the direction of the current. In a simple one like I showed you, it uses physical brushes, and those can be electrically and acoustically noisy and less efficient. A brushless motor electrically looks like this. It has 3 sets of coils. And so to drive it, what you need to do is so this is what's called a half bridge. It's half of an H bridge, and you need 3 of them. So if this is on and that's off, current goes like that. If this is on, that's off, it goes like that. If this is on, that's off, it goes like that. And so in turn, you turn the H bridges on or off in a ring, and then that's how you control what's going into the brushless motor. By getting rid of the brushes, they're more efficient, they're quieter, they're denser. There's many, many, many kinds of them. Hobby King is one of the vendors of all different sorts of brushless motors. So you can get in-runners where the inside turns, or out-runners where the outside turns, pancake ones that are flat, fan ones designed for fans, gimbal ones where to control angle. The outrunners can be more efficient at low RPM, which is why they're common for things like drones. And for scaling, they're spec'd by RPM for volts, and amps and dollars are roughly correlated. So a 1 amp motor you can drive, it costs $1 and you can drive for $1. 10 amps for about $10. 100 amps is a skateboard. 1,000 amps gets to be a car. This is a chip that's a triple half bridge, but far and away most common is these are very commoditized. So ESCs are electronic speed controllers, and these are so commoditized, you can't really make these any cheaper than that. And so you use these, and they take the very same kind of PWM as servo motors, but control BLDCs. So a small BLDC, you can use a triple half bridge chip, but for anything beyond that, we use these electronic speed controllers. Now we're up to steppers. So here is, so right now I'm moving slow and fast, forward and backwards, with a stepper motor. And I've got, I'm doing it two different ways. So stepper motors are like what, is, for example, you'll see them in your 3D printer. Stepper motors, so conceptually, they're just two sets of coils. And so we need two H bridges for each of the coils. What's actually going on is, so the coils are interleaved like this. So it's two sets of interleaved coils. And then here we have north-south, north-south magnets. And so depending on which coil is energized, there's one orientation where it's happy. Then when you energize the next set of coils, it's unhappy and has to rotate to realign. So the stepper is specified by that step direction to align the coil, and 1.8 degrees is typical. And so this, well, actually, let me do the opposite order. In this example, here's the H bridge that we used for the DC motor. And now the only difference is I've got two H bridges rather than one. And then I'm going to send the steps into the motor. Then this is such a common thing to do. This is a favorite part. It was out of stock through the pandemic, and it's now back in stock. And so what's in here is all of this. Good. So in this busy diagram, all of this side is the H bridge. Next to that is the controller for it. And then this has what's called a step and direction interface. So in the example with just the H bridges, in software, I'm firing the pulses to make the step. With this chip, it's much easier. All you do is you send a pulse. You have a signal to say which direction you want to go, and you have a pulse to say make a direction, and it knows how to do that. And not only that, it knows how to do something really valuable called microstepping, which is rather than having the coil be all on or all off, you can vary the current to the coils, and that makes it move more smoothly. And this knows how to microstep down to 250 microsteps. And so with that one, it's much easier to drive. All you do is you just say make a step, and it does all of the rest. Yeah, I'll talk about some of the other chips in a moment. And so that's how you drive step. Actually, we're right up to that. So that's how you drive steppers. There are Trinomic is oh, I see. They were acquired by Analog Devices. That's more recent. They make chips that are optimized to be very quiet. And there's a question in the chat about quiet steppers. Oh, yeah. There's a link in the chat that's very important that I missed, that I'll explain. The quiet steppers, those are nice, but you can do it in software. So with the micro stepping on this and with micro stepping on this, you can implement quiet steppers on any of these as long as you can micro step. The link in the chat is a one that I should have linked, which is, I want their video. So what this is doing is it's getting rid of all of the mechanical linkages, and it's taking a stepper and just unfolding it flat. And so the motor, oh, this is a whole unboxing, but once it starts running, the motor is just a linear array of magnets. Yeah, so you can unfold the stepper and make a line of magnets to make a linear motor. We're almost out of time. If you want to switch AC loads, we use what are called hockey pucks. On one side is the AC load, on the other side is a low voltage signal, and those are optically isolated, so they can't talk to each other. You switch the high side to be safe, and that's how we switch AC loads. You can also get switched outlets. And then this is a science paper on how to make artificial muscles out of fishing line. This is a student project using that to make artificial muscle actuators that can do that. And this is a news story on a student who works in my lab on making shape-shifting fibers to make artificial muscles. And then if you make inflatable structures, you can. These are former students, and here they're controlling the air pressure to make this inflatable actuator. So with that broad tour, and let's see, Adrian is showing lots of examples of driving these in the chat. Pick an output device. It can be LEDs, it can be screens, motors, it's actually not crazy to wind your own solenoids. If you want to, you can play with artificial muscles. Pick an actuator an output that's relevant for your project. As a group, measure the power consumption. And again, for the USB, you can simply do it with the USB power meters if you're using that. These you should certainly have around in your lab that let you connect to a USB load and see what's going through it. And then add an output device. And so this is a fun, expressive week. Oh, and let me add really quickly with the featured assignment for this week is Ling Dong, who fell in love with the OLEDs, and he went crazy with them. So he made a whole menuing system. And he started, let's see, this is doing 3D rotations. Here he's going to rotate Stanford teapot. This is all running on a SAMD processor. Yeah, it goes on. I won't take all the time. He does all sorts of examples of cool things with the screen. And for extra credit, the way the board looks has nothing to do with the function. He just got into how the traces look, and he just wanted to make lots of traces that look cool. But he does a beautiful example of all sorts of showing the power of what you can display on the OLEDs. Okay, so with that, use the open time on Saturday. Do come to the machine building recitation. We're going to apply everything I just covered to learning how to make machines. And with that, happy machine building. And this is a fun, expressive week. I look forward to seeing what you accomplish next week. Bye-bye.
Hey.
Bye.
Plus, tack för det.
Vi syns. Bye.
Bye.
zobaczenia. Pozdrowienia z Wrocławia.
Bye, też się